Welcome to This Explainer. Today we're taking what looks like incredibly dense, impenetrable nuclear physics and transforming it into something, well, much more relatable. Think of it like a simple game of subatomic target practice. If you've ever stared at a nuclear engineering text and felt your eyes just instantly glaze over, you are absolutely in the right place. We're going to strip away all that complex jargon and explain everything in a much simpler way.
Okay, here's our roadmap for today. We're going to cover Section 1, the subatomic target practice. Then Section 2, bouncing off with elastic scattering. Section 3 is the catch, also known as radiative capture. Section 4 covers energy minimums for inelastic reactions. And finally, Section 5, controlling the core. Let's dive right in.
All right, Section 1, the subatomic target practice. To get started, we really need to understand the absolute central concept of this whole subatomic arcade. Everything we're talking about today revolves around one fundamental rule. And that concept is the microscopic cross-section. Now, when you hear the word cross-section, you probably picture, cutting an apple in half and looking at the physical slice. But in nuclear physics, that's a trap. The crucial point here is that a cross-section isn't a physical slice of an atom at all, it's really just the mathematical probability of a hit. Think of it like a virtual target painted right on a nucleus. Depending on exactly how fast our projectile, the neutron, is moving, that virtual target might appear huge and easy to hit, or it might shrink down to a microscopic speck. It's all about probability.
Moving on to Section 2, bouncing off, or elastic scattering. In our arcade game analogy, this is basically just neutrons bouncing off atoms like tiny billiard balls.
Now take a look at these elastic scattering cross-sections. Notice those crazy spikes on the right side? If you're just glancing at this data for the first time, it looks deeply intimidating, right? Like a heart monitor totally gone haywire. But I promise you, it actually follows a very clear, simple pattern once you know how to read it.
Let's break that down simply. On the left side, where the neutron's energy is low, the lines are flat, smooth, and constant. The probability of the neutrons bouncing off the nucleus is totally predictable. Physicists actually call this potential scattering. But as you track to the right and that neutron gets more energetic, meaning it's moving much, much faster, the interaction gets wildly chaotic. The virtual target size violently spikes up and down. We call these wild spikes resonances. Eventually, though, at extremely high energies, the chaos settles down, and the probability starts a nice smooth fall. But even in the middle of all that high-energy chaos, there's a really fascinating detail. If you look incredibly closely at those spikes, there are tiny dips right in front of the peaks. The target size actually shrinks right before it massively expands. Why does it do that? Well, it's because of quantum mechanical interference. In the strange quantum world, the particle can actually act like a wave and literally cancel itself out right between the smooth potential scattering and the chaotic resonance scattering. It's just a beautiful, mind-bending little quirk of quantum physics showing up right there in the hard data. Okay, Section 3, the catch, or radiative capture. If elastic scattering was all about bouncing, radiative capture is when the nucleus completely absorbs the neutron. It literally just swallows it whole. Tracking this capture probability for different elements, look at how the line swoops dramatically downward as you move from left to right as the energy increases on the bottom axis. And this beautifully illustrates what we call the 1/v rule, which honestly is just a mathematical way of stating something highly intuitive. Think of the nucleus like a baseball catcher. A slower-moving neutron, over on the low-energy side, is like a gently tossed baseball. It's highly likely to be captured, right? It's an easy catch. But a fast neutron, on the high-energy side, is like a 100-mile-per-hour fastball whizzing by. The catcher has a significantly lower likelihood of grabbing it. So a slower-moving neutron is much, much easier for the nucleus to catch.
To really prove this to you, let's look at a simple math problem in 3 easy logical steps. Step 1, we start with a slow neutron at 0.04 electron volts. An electron volt is just a tiny unit to measure its energy. And at this speed, its target size, its probability of being caught, is 100 barns. By the way, think of a barn as the subatomic version of hitting the broadside of a barn. It's literally just a fun way physicists measure the area of our target. Anyway, Step 2, we apply our slower is easier to catch rule, which formally states that probability varies inversely with the square root of energy. Step 3, we calculate the new probability when we crank the energy way up to 4 electron volts. So what happens? The probability plummets from 100 barns down to just 10 barns.
Look at what just happened there. By increasing the neutron energy by a factor of exactly 100, Going from 0.04 up to 4, the probability of it being captured dropped by a factor of exactly 10. Because the rule relies on the square root of the energy, a massive speed increase means a drastically smaller target for capture. It's a perfectly elegant mathematical relationship.
Moving right along, Section 4, Energy Minimums for Inelastic Reactions. This is our third game in the subatomic arcade. This is where a neutron hits the nucleus, but it hits hard enough that it actually leaves the target nucleus in a jittery, excited state.
Notice something vastly different about the inelastic scattering for manganese and iron here? The probability lines don't even start until you're halfway across the energy axis. There is absolutely zero probability on the left side.
This brings us to a super crucial concept, the threshold reaction. Let's compare our two types of bouncing for a second. With elastic bouncing, there's no minimum energy required at all. A neutron of any speed can bounce. But inelastic bouncing, that requires an entry fee. If the neutron doesn't have a minimum amount of energy, the reaction simply cannot happen. I mean, the probability is literally zero. But if it does meet the threshold, it bounces off and transfers enough energy to leave the nucleus physically excited.
What's absolutely fascinating is how this rule changes depending on the size of the atom you're hitting. Heavier nuclides, like uranium-238, have a much lower energy threshold. We're talking around 50 kiloelectron-volts compared to lighter atoms. Their entry fee of energy is much, much lower. And this is incredibly significant because it means heavy elements are far more prone to this type of excited reaction at lower energies.
And finally, Section 5, Controlling the Core. So we've talked all about bouncing, catching, and exciting these nuclei. But why does this actually matter to you and me? How do scientists actually use these subatomic probabilities in the real world?
Well, they use them to build and safely run nuclear reactors. By understanding these very specific cross-sections, these exact target sizes, engineers can choose materials to do highly precise jobs. For example, cadmium and boron-10 have incredibly massive capture cross-sections. They're essentially giant subatomic baseball gloves. That makes them the absolute perfect candidates for control rods. If a reactor gets a little too hot, you just drop in the cadmium, it effortlessly catches those flying neutrons and safely slows the reaction right down. On the flip side, we can use the capture probabilities of uranium-238 or thorium-232 to intentionally absorb neutrons and breed brand new usable nuclear fuel. We are literally utilizing pure probability to engineer our energy grid.
And that brings us to the end of our roadmap, leaving you with, I think, a pretty profound thought. We've seen that the invisible subatomic world is entirely governed by these incredibly precise speeds, rules, and probabilities. A neutron moving just a fraction of a second faster can change a reaction from a guaranteed catch to a complete miss. It really leaves you wondering, if everything relies on exactly how fast these tiny, invisible particles are moving, just how delicate is the masterful engineering balance required to safely power our modern cities? It's a high-stakes game of subatomic target practice, and our engineers have to hit the bullseye every single second. Thanks so much for joining me on this explainer. I really hope this helped make a complex world a whole lot simpler.